Kia ora team, welcome to the 2022 reactivity exam, which is worth 4 credits, so let's smash into it. Question 1, hydrogen iodide. Let me get my little tool here. Hydrogen iodide can be produced through the reaction of hydrogen gas with iodine gas, as shown in the equation below. Here's the equation, write the Kc expression for the reaction. Okay, here's what I want you to think about. Kc is a fraction, okay? It's an equilibrium constant. It tells us the ratio of products to reactants when the system is in equilibrium. What is equilibrium? Equilibrium is when the forwards reaction is going at the same rate as the backwards reaction. So if Kc shows the proportion of products to reactants and it goes in a fraction, what is this Kc expression going to be? Have a think, have a go. Pause the video if you want. Okay, so Kc is usually got the concentration of the products at the top of the fraction and the concentration of the reactants at the bottom. So this is how we do it. So we've got our products up top and our reactants in square brackets down below. Remember square brackets for concentration? And when you have a big number, that becomes an exponent. Okay? Cool. Next question. That was worth and achieved, by the way. At 490 degrees Celsius, the equilibrium mixture has a concentration of 0.105 moles per litre for both H2 and I2, while the concentration of HI is 0.711 moles per litre. Calculate the value of Kc. So this is super easy because what we have to do is we just have to substitute things in, which is what I've done here. Alright, so just to explain my process, here I've got the equation, the Kc expression, and I just need to substitute the values that they've given me. So I've got Hi, which they tell us is 0.711, and remember the little subscript at the top. Then down below, I have got the concentrations for both Hi and I, and they're down here, okay? Down here. So both of them are going to be 0.105, and I'm going to times them together, okay? There's no symbol between here, but you should know that these are both being timesed, okay? So plugging this into my calculator, 0.711 divided by these two values here times together will give you 45.9. To 3 significant figures, no units are required, and that's worth a merit. Explain what would happen to the value of Kc if the temperature of the equilibrium mixture was to increase, okay? So I want you to think about these things. So if we have this reaction over here, okay, and we were to increase the temperature of the system, what does equilibrium want to do to the system if we increase the temperature? Well, remember, according to Le Chatelier's principle, whenever there's a change or disturbance, equilibrium or the system wants to counteract that change. So it wants to do the opposite to restore equilibrium again. So an increase of temperature, equilibrium will want to shift in a way that decreases the temperature back down to restore the equilibrium. So which direction is going to be favoured in order for this decrease in temperature to be achieved? Well, if we look at the reaction here, it's important to look at this value. As you can see, it's got a positive delta RH. So what is this going to be? Endothermic or exothermic? It's going to be endothermic. This tells us what the forward reaction is going to be. And according to this, it's endothermic. So knowing that the forward reaction is endothermic, we know that the backwards reaction must be exothermic. So with that knowledge, remember, endothermic means what? It means that it's absorbing heat energy. So this is the reaction that has to be favoured to bring the temperature back down. By favouring an endothermic reaction, that added temperature is being sucked into the reaction. It's being sucked away from the surroundings. So that is what will allow for a decrease in temperature. It cannot be the exothermic reaction that's being favoured, because exothermic reactions produce or give off heat energy, which increases the temperature, and we don't want that. We want to bring it down. So we know which direction is being favoured and why, but the question is also asking us what happens to the value of Kc. Well, Kc is a fraction, remember? So anytime you get a fraction and you get a top-heavy fraction, that increases the value of what it's equal to. Anytime you get the bottom part bigger, that means a smaller value over here. So in this case, because it's a forward reaction being favoured to decrease the temperature back down, what's being produced more, the reactants or the products? The products, because the forward reaction is being favoured. So because there are more products, we're getting a top-heavy fraction, which means a bigger Kc value. So that's what we're going to talk about in our answer. So how have I structured it? Before you see my answer, see if you could give it a go, or even just think about it. So I've referred to Le Chatelier's principle here. According to Le Chatelier's principle, when there is a change or disturbance to the system, the equilibrium will shift to counteract the change and hence restore equilibrium. In this case, if the temperature of the system increased, the system would try counteract this by favouring the endothermic reaction to decrease the temperature back down. So I've given an explanation, which is quite general, but it's important to link it to the context. So, since the forward reaction is endothermic, how do we know it's endothermic? Because of the positive delta RH. This means this reaction absorbs the added heat energy. Therefore, equilibrium will shift to the right. It's important to give the direction of where the equilibrium is shifting to counteract the increase in temperature. Okay. Final part, referring to Kc, by favouring this direction, the concentration of products increases, which increases the value of Kc. And that gets you an excellence by talking about all these things. Hydrogen iodide is a strong acid, whereas hydrofluoric acid is a weak acid. Write equations to show their reactions with water. Okay, a clue for you. Strong acids, okay, such as Hi, are they going to fully dissociate or partially dissociate? I want you to think about that. They're going to fully dissociate. So whenever we have full dissociation of something, remember that arrow is going to be direct, okay, because all of it's breaking up into ions. Because it's an acid, what is it going to do? Is it going to donate hydrogens or accept hydrogens? Correct if you said it's a donator. Acids are hydrogen donators. What is it going to donate it to? It's going to donate it to water. So what would water turn into if it's got an extra hydrogen? Yup, H3O+. So as you can see here, we've got Hi plus... Ooh, what am I doing here? We've got Hi plus water, and it's dissociating it into its ions. So the Hi is donating its hydrogen to the water to turn it into H3O+. And because that Hi has lost a hydrogen, it has a negative charge. Okay? So, the next thing you're going to do is you have to draw a reaction for hydrofluoric acid. It's a weak acid. So is it going to fully dissociate or partially dissociate? It's going to partially dissociate, which means that we have to use what kind of an arrow? An equilibrium arrow, to show that some of it is actually still remaining intact. So, if we look at the reaction, here's what we do. It's still an acid, okay? It's still going to donate its hydrogens to H2O to turn into H3O+. So, that process is still similar to the one up top, but the only thing changing is the equilibrium arrow. So well done if you got that. Okay, Next question, solutions of both hydrogen iodide and hydrogen fluoride are made up to the same concentration. Explain how pH and electrical conductivity of the two solutions would differ. So, what to do here? We need to talk about pH and what that is. We need to talk about electrical conductivity, what that is. And then we have to talk about these in context to the question. That's what gets our excellence. So, let's start off by simply stating what these depend on. So, pH is a measure of hydronium ion concentration. Okay? And electrical conductivity depends on the concentration of free-flowing charges in the solution. Okay? If something doesn't have free-flowing charges, it cannot conduct electricity. So this is what electrical conductivity depends on. So now let's talk about it in relation to HI and HF to get our extra points. So I'm starting off with HI. Since HI is a strong acid, it will fully dissociate into its ions and produce more H3O+. This will account for a lower pH. Remember, the more H3O+ ions there are, this means a lower, more acidic pH, and you have to state that. And because it's full dissociation of ions, there are more free-flowing charges. There's a greater concentration of free-flowing charges, which means that there's going to be greater electrical conductivity. So that's what I've written here. Now, it's a compare and contrast, remember, so I'm comparing with HF. So in comparison, HF is a weak acid, which means that it will only partially dissociate into its ions. So because of that, because of the partial dissociation, there's going to be less H3O+ formed, and that means there's going to be a lower concentration of free-flowing charges and ions because some of it's still intact, okay? So therefore, HF will have a higher pH because it's producing less H3O+, which means that it's going to be less acidic. And on top of that, it's also going to be less electrically conductive than HI. So I've compared and contrasted it. I've defined what pH's electrical conductivity is and referred to the context, which gives you an E. Oh, guys, this is take 2 of this recording because my previous recording didn't record audio, so we're here doing it again. But because I love you all, I am more than willing to stick through. Anyways, back to it again. Question 2. Methanol is manufactured through the reaction of carbon monoxide with hydrogen gas. The equation for the equilibrium that is established is shown below. Once chemical equilibrium has been established, the concentrations of all species present in the reaction are recorded and graphed below. Okay, so we need to explain how the graph shows the system is at equilibrium through section A. Refer to the rates of the forward and reverse reactions in your answer. So, it already tells us that the system is in equilibrium in section A. We just need to justify it. So what's something that you observe about section A? This is the product over here. As you can see, these guys over here are the reactants, okay? But we're just looking at section A. What's something that you notice about these lines? Yup, they are all flat. So what does that mean in terms of the concentrations of each? Yeah, so the concentrations are staying constant throughout this time period during section A. So if the concentrations are the same, this means that the amount of products being produced and the amount or concentration of the reactants being produced are the same throughout this time period. Why is that? How is that possible? Well, it's because the rate of the forward reaction to produce products is happening at the same rate for the reactants to be produced. So because the forwards reaction is taking the same amount of time as the backwards reaction, the concentrations of these things are staying constant. Okay, they're all being produced at the same time, producing the same amount. Okay, so how do we put that into words? The concentration of the products and reactants, I'm being specific here, you should too, are constant throughout section A. So you can see that because of the flat lines. Since the concentration of these species are constant over time, this indicates that the forward reaction is occurring at the same rate as the backwards reaction. So I've talked about this part of the question, tick. Finally, this shows that the system is at equilibrium in section A. So I've showed and explained the graph throughout section A, and I've talked about the forwards and the reverse reactions in my answer to justify why this is at equilibrium. So I've ticked all parts of the question. Moving on for the second time. Don't worry, I'm not salty. At the beginning of section B, in the graph on the previous page, some carbon monoxide, CO, is added to the reaction vessel. Explain using equilibrium principles how the system responds to restore equilibrium. Okay, so what do we have here? We're looking at section B now. Okay, so in section B, as we can see, more carbon monoxide has been added over here. You can see this in the spike. So as more carbon monoxide is added, what do we notice about what's happening to H2CO and the products? Well, we can see that once more carbon monoxide is added, the concentration of the reactants is actually decreasing initially, but the concentration of the products is increasing. How peculiar. Why is this happening? How can you explain this? Okay, how I like to think about it is of two hills, okay? The first hill is the reactant hill. The second hill is the product hill. So, by increasing the concentration of CO, which is a reactant, okay, I'm creating a big boulder, okay? This is increasing the reactant on this hill. This means the product, in comparison, is a little bit smaller. The reactants, because it's a bigger boulder, has a greater mass, so it's going to roll down the hill to the product side to make it bigger. This is how I make sense of it. So, for the reactants which have increased, okay, equilibrium states that by increasing the reactants, the equilibrium will shift to the right to use up the added reactants and increase the products, okay? So to counteract that increase in reactants, we want to use it up, shift the equilibrium to the right to make the products bigger and the reactants smaller, okay? Which is what is shown here. When more reactant is added, can you see that the reactants is decreasing over here while the products is increasing, okay? This is all to do with restoring equilibrium, okay? So in my answer, what am I going to say? Well, when CO is added to the reaction, this increases the concentration of reactants. The system responds by shifting the equilibrium to the right to favour the forward reaction, be specific with your directions, which decreases the concentration of reactants, be specific, and increase the concentration of products, again, be specific. So anytime you need help visualizing what happens if you increase or decrease the concentration, think of these hills over here. What one's the bigger boulder? Which direction is it going to roll in? Okay. Similarly, if I, just for learning's sake, if I had a big boulder on the product side, it's a huge boulder, what direction would equilibrium go in? It would go to the left, okay? Because we want to use up the added products to decrease this stuff and increase this stuff, okay? And that's how even things out and make things reach equilibrium, okay? Anyways, going back. Let's finish this question for the second time. I'm not salty. This is shown in the graph. When CO is added, initially the concentration of CO and H2 decreases, as we can see here. While the product, CH3OH, increases. This forward reaction is favoured until eventually the concentration becomes constant as the equilibrium is re-established, which is shown in section B. So I've talked about what happens initially when the reactance is increased, when there's more CO added. And then I talk about this phase here. Once equilibrium is reached, okay, everything levels off. Okay, we're back to equilibrium here. After counteracting the increase in reactance, okay, by favouring the forward direction, we reach equilibrium again, okay? And that is worth an E. Using equilibrium principles, explain why carrying out the reaction at high pressure is advantageous to the manufacturer, okay? We have to talk about these three things here. So it's another equilibrium question, but this time instead of concentration, we're talking about pressure. So here's what I want you to think about. If we're increasing the pressure of the system, what does equilibrium want to do to counteract that? It wants to bring the pressure back down. It wants to counteract that. How? Think about it. Well, it has to decrease the pressure by shifting in the direction which has the least amount of gaseous moles, okay? Because less gaseous moles means less pressure, and more gaseous moles means more pressure. If we're visualizing that, think of these two boxes, okay? If something has less gaseous moles, there's less pressure. If something is crowded with lots of moles, there is going to be more pressure. More moles, more pressure. Less moles, less pressure. In this case, we want to decrease the pressure to counteract the increase, so we want to favour the side with the least number of moles. In this case, in this reaction, which side has the least number of moles? The products or the reactants? The products, there's no 1 written here, but we can assume that because there's no number here, there is 1 mole of products and 1, 2, 3 moles of reactants. So equilibrium is going to favour this right-hand side, forwards direction reaction, because it has less moles, which means less pressure. Okay, and we want less pressure to counteract the increase in pressure. So, why is this advantageous to the manufacturer? Well, by increasing the pressure, have a think of what happens. The forward reaction is favoured, which means that we're driving the production of more methanol, which is what is advantageous to the manufacturer. So let's answer these 3 things. So, when the pressure is increased, the system opposes this change by favouring the side with the least number of gaseous moles to decrease the pressure. Make sure you include gaseous moles. Whenever we're dealing with pressure equilibrium questions, have this keyword. Okay. Now we have to be specific. We need to count the number of gaseous moles and specify that. Specificity is so important. In this reaction, there are 3 gaseous moles of reactants and 1 gaseous mole on the product side. Therefore, equilibrium will shift to the right to favour the forward reaction. I'm being specific with direction, or product formation. This accounts for a decrease in pressure. Why? Because it has less moles, which means less pressure. And feel free to add that to extend your explanation. I would. Okay. By driving the forward reaction, more methanol is produced, which is advantageous to the manufacturer. Okay. So we've done this, this, and this, and you've got yourself an excellence, my friend. Let's move on. The formation of methanol from carbon monoxide and hydrogen gas is a slow reaction. To increase the rate of reaction, a small amount of zinc oxide can be added. This zinc oxide can be recovered after the reaction is complete. State the role of zinc oxide in the reaction. Okay, well, whenever you have something that's increasing the rate of reaction, it's not used up, what is it? It's a catalyst. Okay, easy peasy. An energy diagram for the reaction without the use of zinc oxide is shown below. Add a line to show how the diagram would differ when zinc oxide is added. So, we've already established zinc oxide is a catalyst. So what do catalysts do? Correct, they offer an alternative pathway that has a lower activation energy threshold. What is activation energy? It is the minimum amount of energy needed for a reaction to happen. So let's draw that in. Let's draw another pathway starting at the same point, except this time, let me connect that up a little bit better. We have a lower activation energy, okay? And we're ending at the, oh, that's not what I want. Let me draw that a little bit better. Ending at the same point. I'm sure your diagrams will be a little bit better than mine. Anywho, important to label this as ZNO catalyst. And the activation energy, as you can see, is a lot lower compared to, what am I doing? Is a lot, oh gosh, is a lot lower compared to this reaction without the catalyst. Okay, and that's worth an achieved. Okay. Explain how zinc oxide increases the rate of reaction. Refer to collision theory and activation energy. As you can see here, when I first recorded this exam, I left a few scribbles here. Okay, thank my past self for doing that. So, these are the key points that we need to refer to in our answer. How does zinc oxide increase the rate of reaction? And how is collision theory involved? And what is the role of activation energy in this whole thing? So, as I've mentioned, zinc oxide, this catalyst, increases the rate of reaction by providing an alternative pathway, AP for short, alternative pathway, which has a lower activation energy. We don't want to say zinc oxide lowers the activation energy. No, I would rather you say that it provides an alternative pathway which lowers the activation energy. So how, we have to explain how that actually speeds up the rate of reaction. Well, by providing an alternative pathway with a lower activation energy, the proportion of reactants, a greater proportion of reactants have enough activation energy to collide together to form products, okay? So, let me explain. Think of these lines over here, without and with catalyst, as a little bit of an analogy. Okay, I love my hills, so I'm going to use a hill analogy. So, pretend you are on a journey taking NCA, okay? And so, without Miss G, without me, okay, pretend I'm the catalyst, without Miss G, you are going to have to climb this huge hill and teach level 2 chemistry all by yourself, okay? So, if that were the case, out of, say, 10 of you, only 2 of you might actually pass or get excellence, okay? But when you add the catalyst, aka Miss G, which is me, the hill for achievement becomes a little less steep. It becomes less steep and easier to climb, okay? So with Miss G's help, this hill is flattened. Miss G has squashed this hill for you, okay? She's provided you another alternative pathway to learn faster and better, which means more of you can climb this hill, overcome it, and pass or get endorsement, okay? So that's what the catalyst does. It increases the proportion of particles, increases the proportion of reactant particles, and ensures that they have sufficient activation energy, okay, to overcome the activation energy threshold, okay? So they have enough energy to collide and overcome this lower threshold, okay? So how do we talk about this in our answer? So, zinc oxide increases the rate of reaction by providing an alternative pathway with the lower activation energy. Activation energy is the minimum amount of energy required to start the reaction. By having a lower activation energy threshold, as you can see over here by the red line, a greater proportion of reactant particles, I'm specific, can collide with enough energy to overcome the activation energy threshold. So I've referred back to collisions, okay? This results in a higher frequency of successful collisions and therefore an increased rate of reaction. Something that you could add is more detail on collision theory. So you can state that for successful collisions you need the correct orientation and enough energy. Okay, that's a good way to define collision theory. And by providing an alternative pathway with a lower activation energy threshold, a greater proportion of particles have sufficient energy to collide and overcome the activation energy threshold, and therefore increasing the successful frequency of successful collisions and increased rate of reaction. Boom, 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 done all of these, and so that would get you, I'm pretty sure it's an excellence, but we'll have to double check that on the answer schedule. I will link that in the comments below. Okie dokie, calculate the concentration of hydronium ions in a solution of hydrochloric acid that has a pH of 2.4. How do we calculate the concentration of hydronium ions? Well, the equation that's given to you in your resource sheet is this one over here. All you have to do is plug in what we have, which is the pH, into this over here, substitute that in, plug this into your calculator, and you should get this value. And remember, 3 significant figures. Zeros aren't counted as significant figures unless they're in between non-zero digits, and don't forget the units as well. A solution of lithium hydroxide has a concentration of 0.450 moles per litre. Calculate the pH. pH, remember, is a concentration of hydronium ions. LiOH, lithium hydroxide, is not providing H3O plus ions, it's providing OH minus ions because it's a base. So we cannot use this concentration, of OH in our pH equation. So we have to find out the H3O plus concentration based on the OH concentration over here. How do we do that? Well, we use Kw. Kw shows the ratio of OH ions to H3O plus. We have the OH, so we could substitute that in, rearrange to find H3O plus, and boom, plug that in. Remember, Kw is a constant, so it's going to be 1 times 10 to the power of negative 14. So let's go ahead Substitute everything in, rearrange to find H3O+. Have a go yourselves before I reveal the answer. So over here I've got the Kw equals the OH minus concentration from the question times H3O+. This is what we want to figure out. So to rearrange to get H3O+ all by itself is I have to divide this whole side by 0.50, cancel it out, and that means I have to do the same on the other side, and then I will be able to work out my H3O+ concentration. Now what I can do is I can plug this in to this equation here. So pH is the negative log of H3O+ concentration, and that gives us a pH of 13.7. Not too bad, is it? Whenever you're given, yeah, I'll just leave it there. You get the gist. Okie dokie. 3 solutions of equal concentration, A, B, C, were known to be sodium hydroxide, sodium chloride, and sodium carbonate. The pH of each solution was measured and recorded below. So, solution A, 11.6, solution B, 13.0, solution C, 7.0. Which one's which? Which one is which? Well, we've got a clue here. We've got the pH values. So, as you can see, solution B has the highest pH. Because it has a high pH value, this means it's more basic. This means that there is a high proportion of OH minus ions and very little or none of the H3O plus ions. Okay? So, this must be a strong base. Out of these three solutions, which one could be the strongest base? Which one is going to provide a lot of OH ions? Yep, NaOH. It's got OH in it, as you can see. It's a strong base. It will fully or partially dissociate. Which one is it going to be? It's going to fully dissociate into its ions because it's a strong base, and so it'll release heaps of this OH, which accounts for this high pH, which is very basic. Okay, we've got another high pH value, not as high as 13. So what would solution A be? Is it going to be sodium chloride or sodium carbonate? Well, let's look at sodium chloride. If sodium chloride dissociates into its ions, okay, Na and Cl, is Na and Cl acidic or basic as ions? No, neither of them are acidic or basic, so it cannot be solution A. Since sodium and chloride as ions are not acidic or basic, it has to be neutral, which is solution C. Okay, which leaves us with sodium carbonate. So sodium carbonate is a salt, like sodium chloride, okay? Both of these are salts. However, with sodium chloride, it has a 2-step dissociation process. First, it splits up into its ions. Then the carbonate acts as a weak base, which then is able to produce some OH minus ions, and we're going to see that very soon. So it must be solution A. Fully explain how you identified solutions A, B, and C. So if you need to rewind and listen to how I've explained what is what, have a go and try write the answer yourself. Otherwise, just follow along with me. Okay. So as well as explaining what solutions what, we also need to use relevant equations. So this is when your balanced equation skills come in handy. So first things first, I want to define what pH is first of all. Let's set the scene. pH is a measure of hydronium ion concentration. The more acidic the solution, the greater the concentration of H3O+, and the lower the pH, as I've shown over here. Okay? The more basic a solution is, the less H3O plus and the more OH ions there are in solution, therefore a higher pH. NaOH is a strong base, which means that it fully, bit of a typo there, it fully dissociates into its ions. This produces a high concentration of OH minus ions, which result in the highest pH of 13 of all three solutions. So I've compared it to the other solutions. So the reaction for that is over here. We've got NaOH, and then we are fully dissociating, hence why we have a direct arrow, into its ions. Remember the charges, don't forget those. Okay. Now I'm going to focus on Na, that's meant to be A, Na2CO3, sodium carbonate. So I've explained that it's a salt which dissociates into its ions first. How do I show that? Okay, so I've got sodium carbonate, and it's fully dissociating into its ions to begin with, okay? So we've got Na and CO3. To balance this, as you can see on this side of the arrow, I've got Na2, which means that there has to be 2 Nas on this side, so that's why I've popped a big 2 in front of it. Only ever add big numbers when you're balancing. CO3, we've only got 1 on this side, okay? 1 lot of CO3 on this side, which means 1 lot of CO3 on this side. And other charges balanced finally. We've got 2 plus and 2 minus. They balance each other out. Everything is balanced. Good job. Okay, so it's a salt. Its first step is dissociating into its ions. And the second step is the carbonate, okay, CO3 2 minus, partially dissociates as it is a weak base. Okay, so we've taken this, it acts as a weak base, and so we use equilibrium arrows. So what it's done is it's reacting within water, and because it's a base, it's going to accept a hydrogen, and by accepting a hydrogen, it turns into HCO3 minus. It's a minus charge now because it's gained a positive hydrogen. So that means it goes from 2 minus to 1 minus. And then because it's taken away a hydrogen from water, the water turns into OH minus. Okay, everything is balanced, and that shows how this weak base over here has given us some OH minus ions. Okay. This provides a small amount of OH ions due to the partial dissociation of CO3 2 minus. It's a weak base. As a result, this leads to a basic pH of 11.6, which is lower than NaOH because it's a weak base. It only partially dissociates. All right, last but not least, sodium chloride is also a salt like sodium carbonate and dissociates into its ions. Let's have a look at what this looks like. So we've got NaCl dissociating into its ions. As I've said before, since neither ion is acidic or basic, the solution remains at a neutral pH of 7, okay? That's how you talk about all of these. Have we fulfilled all parts of the question? Yes, we have. All right, we are up to the last question of this exam. Once identified, the solution of sodium carbonate was then used in a reaction with hydrochloric acid. The equation is shown below. The reaction was carried out at both 25 degrees and 50 degrees, and the volume of CO2 gas produced was recorded on the graph below. So at 50 degrees, as you can see, this is a lot steeper than this line over here. So what does this mean? What does a steeper line indicate? A fast rate of reaction, okay? So that's the initial observation that you should make. Okay, then we have to discuss that. So in both reactions, the same concentration and volume of each solution is used. Explain the effect of increased temperature upon the rate of reaction. In your answer, you should refer to collision theory. I feel like pink. Collision theory. Consider both the rate of CO2 production, the rate, and the total volume formed for each reaction. refer to the lines on the graph above. So these are the things that we have to tick off. It's always good to highlight what you need to write in your answer and talk about each thing in a good amount of detail. So, as I've explained, bit of an oopsie there, dropped my iPad, we're all good. So, as you can see, as I've explained before, we've got the reaction occurring at 50 degrees, and it's a lot steeper, and it's a faster rate of reaction. All right, we're going to have to refer to collision theory and why we're observing what we're observing. Okay, so what do we talk about first? I've defined what collision theory is all about, okay, in this upcoming piece. So, successful collisions occur when reactant particles come together with correct orientation and enough energy. That's what collision theory is about. So, when the temperature is increased, the reactant particles, I'm specific here on what the reactant particles are, obtain more heat energy. Then this heat energy, as the particles gain more heat energy due to increased temperature, this is converted to kinetic energy. So the particles, the reactant particles, are moving around and jostling really fast. This allows the reactant particles to jostle more, which results in more likely collisions per unit of time, hence an increased rate of reaction. You just think about a little room. Think about there being a bunch of, say, year 9s, okay, and they've got a lot of energy, okay. Because they have a lot of energy, they are going to collide with each other a lot more than if they were traveling really slow, okay. So by increasing the temperature, you increase the heat energy of the particles, and that gets converted to kinetic energy and results in more likely collisions per unit of time. Hence, increased rate of reaction, okay? So, I want you to be aware that there is another factor. By increasing temperature, you also speed up the rate of reaction in another way besides providing more kinetic energy, okay? So another way increased temperature speeds up the rate of reaction that you should know and mention is by allowing for a greater proportion of collisions to have enough energy to overcome the activation energy, okay? So it's kind of similar to my activation energy catalyst explanation, okay? But in this case, it's the collisions that have a greater proportion. It's a greater proportion of collisions, not particles, that have enough energy. Okay, so you have to be clear with that distinction. So, greater proportion of collisions have enough energy to overcome the activation energy. Okay. So, this results in an increased frequency of collisions and increased rate of reaction. All right. This is depicted by the blue 50-degree line, which shows a steeper curve. So I'm up to this part here. I'm actually going to come back to this soon, but I'm referring to the lines to begin with. Okay. So this is depicted by the blue 50-degree line, which shows a steeper curve than the red line at 25 degrees. This steepness indicates a faster rate of reaction where CO2 is produced faster than the reaction carried out at 25 degrees. Although the rate of CO2 production is higher at 50 degrees, by the end of the reaction, the volume of CO2 produced is actually the same as both lines on the graph end at the same point. So you may be tempted to say that a greater volume of CO2 is produced. Actually, it's producing the same amount by the end of the reaction, but it's just being produced at a faster rate. So it seems like at this point the concentration of CO2 produced is less okay, is less. But by the end of the reaction, it's actually the same for both of the lines, okay? So the volume of CO2 is going to be the same by the end of the reaction. It's just faster for the 50-degree reaction, okay? So we've referred to this, we've referred to this, we've referred to this, and we've also referred to the lines on the graph. So we've ticked every single thing. We have finished this exam. Thanks for listening. Hope it was helpful. Please feel free to reach out, comment anything that you don't understand, and I will get back to you. But all the best for your study and exams.